In this video, we're going to talk about association between quantitative variables. So in the first part of chapter 2, we talked a lot about how we graph and how we summarize one quantitative variable. Now we're coming back to what we covered a little bit in chapter 1, which is how do we describe, how do we plot, how do we summarize two quantitative variables. I'm sorry, I think I said categorical before. I meant quantitative. We're dealing with quantitative stuff here. So when I have two quantitative variables together, how do I look at the association between them? We did that a little bit in chapter 1, but we're adding to it. We're adding to it now. Okay? And so we're looking to describe the association between those two variables. We're going to plot the data using a scatter plot, which we did define in chapter 1. Okay? And then when we look at that scatter plot, we can do a couple things. Also described in chapter 1 was this direction of association. Is it positive or is it negative? So a positive association means when values of the explanatory variable increase, the response variable also increases. That looks like this. Negative association, it goes down. So this slide was from chapter 1. Now, excuse me, what I'm adding now in chapter 2 is that we are going to, or we can, describe the strength of the association. And we can do that numerically. And the numerical thing that does that when two quantitative variables seem to have a linear relationship, and that's a very important part. This only works if it looks like the data has a linear relationship. If that's true, and I guess also I should say a linear relationship means that it looks like if I drew a line through the points, that line would fit the points well. It's that the data isn't some weird shape. It looks like it's the trend is happening, like the points are moving the same way the entire time. And if the data does do that, we can summarize the strength of said association, either positive or negative, with the correlation. Now, the correlation, or specifically the correlation coefficient is what it's called. It's denoted by a lowercase r in this class. So lowercase r is the correlation, and the correlation ranges from -1 to 1, where -1 is a perfect negative relationship, and +1 is a perfect positive relationship. So -1, perfectly negative, +1, perfectly positive, and then in the middle, you've got 0, which is no relationship whatsoever. As x increases, y does not do anything. Okay? And now, I don't want to be too scary, but here's the formula for the correlation coefficient. I'm definitely not going to make you ever calculate the correlation coefficient by hand, okay? But there it is, if you ever do want to go back and look at the formula. Okay? And so here are some examples of what the strength of association might look like. And so perfectly positive is the data literally forms a line going up and to the right. Perfectly negative is the data forms a perfect line going down and to the right. Okay. 0 is that thing in the middle, or rather, the top right picture, where there's nothing happening. The data is just, it's out there, and it, as x increases, as you look at the picture from left to right, I couldn't tell you whether the data is going up or down. It's just everywhere. Okay. And then you get the stuff that, well, I guess the data that actually happens, that you're actually going to see. You'll rarely see the top 3. You'll often see things like the bottom 3. And so the sign in front of the number, either negative or positive, tells you if it's a negative or positive relationship. So the bottom right picture, you see the data is generally going down and to the right, so it has a negative in front of the number. And the first two, the bottom left and the bottom middle, as you're looking at the picture from left to right, the data tends to go up as you go left from right. So the number is positive. So as you look from left to right, if it goes down, the number is going to be negative. If it goes up as you go from left to right, it's going to be positive. And the closer the points are, i.e. the stronger the relationship, so the closer the points are, the closer the number, or the closer the correlation is going to be to 1 or -1. And the more spread out the points are, the closer the number is going to be to 0. So notice bottom left to bottom middle. The bottom left picture, those points are pretty close to each other, and going up, there's not a lot of variability. Whereas in the middle bottom picture, it is generally going up and to the right. The trend is up and to the right, but it's a lot less pronounced. There's a lot more variability there. And so you have two things to worry about for strength of association. Direction, is it positive or negative? And then also strength. So I have I describe it here as a cool web-based game. Okay? I don't know if it's necessarily cool, and I always do this in class. So I'll click this game. It's called Guess the Correlation, and it's going to give you a number of scatter plots. It gives you a scatter plot and asks you to guess the correlation. And so sometimes I sometimes will brag that I'm really good at this game, and then sometimes it looks like I actually am, and other times it looks like I'm terrible. And because I'm sick, I might not be on top of my game, but let's try it. So we're gonna. So I'd ask you for a username, and I made a random one. Okay, and so here's the picture. And so I don't have. Usually we could come together as a consensus and make a guess. So this is definitely positive, and it looks pretty strong to me. So I'm going to say 0.75. And it was really 0.73, so there I made myself look good. But and we'll go next and see if this is stronger than the last one, so also positive and stronger. So I'm going to go with something like 0.9. Right? Again, I'm making myself look good here, but I promise sometime I'll be terrible. Okay, now we have this picture, which is a lot less as strong as the other two. And so, although it might be generally up and to the right, it's a lot less strong. So I'm going to go with something like 0.3. Okay, so there I was too far away. It was 0.4. Then I guess 0.3, so I lost a life. So you have lives, and you can calculate points here. And you can continue on. I'm sorry. This is like almost nothing, so I'm going to guess maybe like 0.1. 0.07, so I got a life back. And you can continue on. Ooh, there we go. This is very strong. Maybe something like 0.97, 0.99. All right, so anyway, I'll stop playing this, and I'll let you play it if you're really bored, okay, and see what kind of high score that you can get. But I hope that gives you a sense of correlation and what the numbers might be. Okay, and then we're going to end chapter 2, with examining categorical data. So, excuse me. We talked a lot about quantitative stuff, and quantitative is easy to summarize or examine. I should say summarizing categorical data, not examining, but summarizing categorical data. What kind of graphs do we make for a categorical variable? And so there are three common ones, three that the book uses or the book talks about. And so they are the pie chart, the bar chart, and then the Pareto chart. Certainly you've seen a pie chart before, and certainly you've seen a bar chart. You probably have not heard of a Pareto chart, which is fine. It's a special kind of bar chart. So the pie chart is the one to the left, and as you might guess, the pie chart splits the data up into pieces of a pie, and then it shows them to you. The bar chart counts the number of observations, like a pie chart, counts the number of observations that fall into each of the categories of the categorical variable, and then it counts them, and then it has bars similar to a histogram. Okay? It has bars like a histogram, although it's not binning anything, it's not summarizing anything, it's just counting the number of times it sees that, and then the height of the bar corresponds to how many it saw, or how many were counted. And then a Pareto chart, which is the rightmost one, it's a bar chart, but it's always ordered so that the highest bar is on the left. Okay, so important notes about graphical summaries for categorical data. Although they're popular, most statisticians do not like pie charts. There are a number of people out there that have strong opinions about pie charts. And the biggest gripe that people have against pie charts is that they are hard to read and easy to misinterpret. And so if I told you to take a look, the easy to misinterpret, or rather hard to interpret, is that human brains have a tough time seeing angles. So pie charts are based on angles. Okay? The angle of your section corresponds to what percentage of that category is in the total data set. And humans have a tough time looking at angles and telling the difference between them. For instance, if I told you to look at the leftmost plot and I took away that banana was 30% and grapes were 27%. So if I took those numbers away, would you be able to easily tell me that banana is larger than grape? And I think the answer is yes if you stared at it, but it's probably going to take 5 seconds for you to convince yourself that blue is slightly larger than yellow. Whereas if you made the same chart, use the same data to make a bar chart, okay, humans are good at telling vertical distance. They're just not good at angles. And so you could very quickly tell me that the blue bar would be higher than the yellow bar. Okay, so it's very easy if you look at, I know the writing is very small on the bar chart below, but it's very easy for you to tell me that premium is above very good, even though they're fairly close, and it would take you a lot longer to look at a pie chart and say the same thing. So for that reason, I'm suggesting that you stay away from pie charts whenever you make a chart. Choose something else. Choose a bar chart. And so bar chart's the bottom. We talked about a bar chart, and we talked about a Pareto chart. Now, the other thing that is very important that you don't do when looking at something like a bar chart is interpret that as skewed or symmetric. So a lot of people, early on, I will ask you questions about what you can and can't say about a bar chart, about a histogram, so on and so forth. And for histograms, we learned about saying if it's symmetric or skewed or various things. And you can't say that for a bar chart because the bars are movable. So it wouldn't make sense for me to move bars on a histogram because those bars summarize data in place. But in a bar chart, and this is a perfect example, the bar chart that I showed you in the bottom left, and then the Pareto chart in the bottom, the top right. A Pareto chart is just a bar chart where the values are ordered from left to right. And if I can order the bars in any way I want to, then I can't say anything about if it's symmetric or skewed because I could change the bars. So right now, if you looked at the bottom middle graph and you weren't paying attention, you could say, oh, that data is skewed to the left. Okay, which the bars are trailing off to the left, which is fine. But if I changed ideal to the center, very good and premium beside it, and then good and fair on the other side of it, you could very well say that data is symmetric. So if I just rearrange the bars, it might look symmetric, and the plot is just as valid as it was before. And so a very long soliloquy there. All of that is saying you can't say anything about center, about shape, about variability, about all of the things that we learned before, all of those summaries, you can't say about about categorical data, which is what we're talking about now. Okay. So those are simple summaries, so simple graphs. Next, we get a little more complicated. And we can look at stacked and side-by-side charts or plots. And these are stacked and side-by-side bar charts, okay? And it wouldn't make sense. Stacked pie charts would make sense. So it has to be with bars. I'm sorry, and this is when I bring in more than one categorical variable at a time. All those previous charts were for one variable. Now I have two variables. Again, I want to look at what we learned about before would be a contingency table, okay? And so now basically what we're doing is looking at visual representations of contingency tables. So you could look at these plots. There are three of them. So the top left, bottom, middle are stacked, and then the top top right is side by side. And what you can do, say with the stacked and side by side bar charts, is you can begin to look and say, does the relationship look to be the same, or does it change throughout the different ones? So specifically that bottom middle one. If you look at the bottom middle one, these plots are about loans, which we've talked about the loans data set before. What type of loan it was, so that's joint or individual, the blue and the yellow. And then the different columns, or the different X values here, rent, mortgage, or own, is your house ownership. Do you rent? Do you have a mortgage, or do you own your house? And so then you'd ask, does the type of, so a question that you might ask, does the type of loan seem to change over rent, mortgage, or own? And so in this bottom chart, you could look, and you could say, well, yeah, it looks like a higher proportion of people who have a mortgage take a joint loan than those who own or rent, and such things. The last one that we're going to look at, I know this is a little long of a video, but this is the last slide. These are called mosaic plots. And they look interesting, and they are pretty interesting. And so they are, again, maybe even more visual representations of a contingency table. And where the different colors, so there are colors in these graphs, they represent the different types of ownership: rent, mortgage, own. And then the length of the bars, or rather I should say the width of the bars, represent what proportion of the whole. So if you look at the top left, you'd say most of the people in the data set have a mortgage. Second most is rent, and then there are only a few that own their home. And so that's how you would generally read that plot. The top right and bottom left are the same data, just with the different variables switched on the row and the column. Okay? And so rent, mortgage, own versus was it an individual or joint loan? And so if you look at the different colors represent the rent, mortgage, or own. Okay, the width of the bar in the bottom plot, So the width of the bar represents the type of loan people got. So if you look at the width of the bar in the bottom plot, the vast majority of people got individual loans. There were only a few joint loans. Okay. And what's interesting in that bottom plot is that not only the width, but also the height of the bar matters. So the height is the rent, mortgage, or own breakdown. The width, individual versus joint. And so you can see that the heights are different for individual versus joint. As we saw before, for joint loans, people who, most of them who took that out were people who had mortgages, okay? And for individual loans, there were generally a lot more of them, but also more even split between rent and mortgage, so on and so forth. So what we can do with these mosaic plots, and the reason why I'm taking so much time to go over them, is that there are a few homework questions that ask you to look at a mosaic plot like this and assess, does it seem like those two things are independent, which is what we did a little bit before in chapter 1 with the contingency tables. And so you need to look what I would suggest for you is to look at them. Look at the plots and say, is the breakdown, for instance, the bottom middle plot, look at the breakdown and say, are the proportions of green, blue, and red, are they the same across the type of loan, so individual and joint, and also are they the same across rent, mortgage, and ownership? And so you would say maybe, but probably not, because the blue bar is taller for joint than individual and stuff like that. Okay, so that's the end of chapter 2, and we'll start with chapter 3 later in the week.